Taking backups is so slow. Is there anything we can do about that? Turns out, probably. Welcome to this video on backing up SQL Server. My name is Kevin Fiesel, and I'm the proprietor of Catalxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. We have talked a good bit about the mechanics of database backup and restoration in SQL Server throughout this series. In this video, I would like to focus in on one particular point, and that is how to back up and restore databases faster. The reason for this is fairly simple. Backing up a database takes resources in terms of CPU and I/O, as well as time. If it takes more than 24 hours to complete a full backup, there's no way we could take a daily full backup. Now, backups don't cause blocking, but in busy systems, we often have maintenance windows where we can get away with taking some of the system resources. And when your backups take longer than your maintenance window, well, people start to get cranky. What can we do about it then? Let me duplicate a bit of work that I've done. For you see, dear viewer, I have a full-length presentation entitled Optimizing Backup Performance Using Data Science Techniques. I will leave a link to the presentation details in the show notes below. There is also a full-length recording of the talk that I delivered, and it's available here on YouTube, again, in the show notes below. Because I don't have a full hour to talk about this topic, I'm going to give you the condensed version in this video. But if you want something that's a bit more free-form, maybe a little more rambly, and definitely a lot more data science-y, I can sate that desire as well. Now, let's talk about what we can do to shorten backup windows. First up, remove unnecessary data. If you have a 1 terabyte database, but it turns out that nobody will ever use 99% of that data, you're spending a lot to back up data that nobody wants. It is no secret that database backup and restoration times depend greatly upon the size of the database. Ceteris paribus, it takes longer to back up a 1 terabyte database than a 1 gigabyte database. But even if you can't remove any data, make sure you're compressing the data as best as you can. Are you using page-level compression on indexes where that makes sense? Do you have any tables that really benefit from column store? Any space you save through compression generally makes every backup faster. The reason is that most of the time, backup operations are I/O bound, meaning that we're waiting on read and write operations to disk rather than CPU, network bandwidth, or memory. And I would expect the second biggest wait for backups is network bandwidth, with CPU coming in a distant third for most systems. Your system may be a little bit different, but at least in my experience, that's the pecking order. If you cannot remove data and you are already compressing relevant indexes, you could split data across multiple file groups. This will be good for two reasons. First, you can back up file groups independently of one another. I'm going to have a video on this topic later in the series. File group backup won't necessarily speed up the total amount of time it takes you to back up or restore a database. What it does allow you to do, however, is get critical parts of the database restored and available first, so that end users can access recent and relevant data while you're restoring the older stuff. Second, splitting data across multiple file groups potentially allows you to create read-only file groups. A read-only file group has some inherent performance benefits, but the one we're concerned with today is that you don't need to keep backing it up. If it's read-only, you can take one backup and be done with it. Obviously, this only works in cases where nobody makes changes to the data, but with a bit of planning, you might find significant quantities of data that are read-only in practice. We've already talked about taking differential backups in prior videos. These help bridge the gap between full backups. On busy databases, differential backups can become larger than full backups, so this is not a guaranteed improvement. But in many scenarios, you could switch from daily full backups to weekly or even monthly, and then take daily differential backups to keep the number of transaction log backups you need to restore to a sane number, like, 2,800 or so. The next option is to use newer versions of SQL Server. For example, SQL Server 2017 included changes to how backup I/O operations work, making smaller databases much faster to back up, and even showing a 10 to 20% improvement for databases larger than 100 gigabytes. Considering that this comes with no effort on our part other than using a reasonably modern version of SQL Server, I'd consider this a no-brainer. And for an even more recent update, we have T-SQL Snapshot Backups. If you have a fast enough storage array and are running SQL Server 2022, you can use T-SQL Snapshot Backups for point-in-time recovery. I'll add links to a blog post from Andrew Prusky and a series from Anthony Nocentino covering the topic, as it may be an interesting alternative to the standard form of taking backups using SQL Server's native capabilities. But I would consider this technique outside the scope of this series, so I'm probably not going to cover it in more detail. The final thing we can do is configure backup settings, and that's exactly what we'll do in this video. I just wanted to make mention of all of these other techniques because they are still important. They're just not things I'm going to be able to cover in this video. So let's talk about these backup settings. There are 5 of them in total, though it turns out that some of these have immediate answers. The first setting is block size, which is the physical block size of the storage device to which you are writing your backups. SQL Server supports block sizes ranging from 512 bytes up to 64 kilobytes. But let me let you in on a little secret. Block size for backups really doesn't matter, unless you're writing directly to a tape drive or to a writable CD. And if your data recovery strategy has you backing up SQL Server databases directly to writable CDs, stop. Get help. Next up, we have a pair of settings, max transfer size and buffer count. The max transfer size is the maximum amount of data that we can transfer per operation and ranges from 64 kilobytes to 4 megabytes. Think of this as the size of a bucket. You can only fit so many bits per bucket. As we scale the max transfer size up or down, the size of the bucket and how many bits it can hold increases and decreases accordingly. Meanwhile, buffer count is the number of buckets that you can use for backup, and this is an integer that ranges from 1 to the limit of your imagination, or the limit of your RAM. That said, there are 3 relevant bits of information that I want to include here. First, max transfer size and buffer count are kind of symbiotic settings, and they combine to tell you how much RAM you are allocating for backups. If your max transfer size is 1 megabyte and you have 100 buffers, you're going to allocate 100 megabytes of RAM to take this backup. If you have a 4 megabyte max transfer size and 1,024 buffers, that's 4 gigs of RAM that you're using to back up your single database. That's 4 gigs of RAM you cannot use for the buffer pool, for memory optimized tables, for watching cat videos directly from the browser while you're remoted into the server. Second, and related, it turns out that the real key to performance is less in the specific settings of max transfer size or buffer count, and more in the amount of RAM that you are making available for each backup operation. In my testing, and in corroborating with others who have performed similar tests, it's critical to have enough RAM for the backup operation, but it doesn't really matter how you get to that point in terms of max transfer size and buffer count settings. 50 buffers of 1 megabyte will perform the same as 25 buffers of 2 megabytes in terms of how long it takes us to back up the same database on the same hardware. Now, in fairness, I am using the same with scare quotes because they'll perform within the realm of noise. What I mean by that is, in my testing, I tried different combinations of max transfer size and buffer count that led to the same amount of RAM, and I could not differentiate this combination being significantly faster than this combination. It was all a wash in the noise. The times were so similar within maybe a second of each other that I could not give you a conclusive answer. Also, you have a certain minimum threshold that we need to meet, but adding more RAM on top of that doesn't make your backups faster. What this means is actually it's a good thing because we don't want to allocate 4 gigs of RAM to backing up that database. It's not going to be faster than allocating a smaller amount of RAM. The only way that we could run into a problem here is if we allocate too little RAM. So if I only have, say, 5 megabytes of RAM for this backup, that may not be sufficient, and we could see a significant performance improvement by allocating more RAM, either in terms of increasing max transfer size, buffer counts, or both. The third bit of information is that your storage location may determine your max transfer size. If you're backing up directly to AWS S3, the values for max transfer size change and instead span from 5 megabytes to 20 megabytes. Further, the max transfer size will directly impact how large your maximum backup file can be in S3 or Azure Blob Storage. We'll talk a bit more about that in the next video. For this video, I'm going to assume either that you're backing up to local storage or a SAN, or that your databases aren't so large that the backups would hit those S3 or blob storage limits. The fourth setting is file count, and this represents the number of backup files we're going to write. This turns out to be a nice way of getting extra throughput out of backups, even when your storage speed isn't incredible. My advice for this is try up to 12 files when writing a large backup to a SAN, and up to 12 per drive if you're writing to direct attached storage. Additional backup files won't have a linear improvement, but there can be a considerable performance gain in moving from one file to multiple, especially if you spread this out over several SSDs or NVMe devices. The final setting is whether you want backup compression on. If you are using SQL Server 2017 or later, my answer is that you probably want backup compression on. With older versions of SQL Server, you could run into some weird scenarios with backup compression and transparent data encryption, but that's all well in the past. Now, you might find cases in which backup compression is slower than turning it off, especially if you have extremely fast storage. But if you're running on slower storage, compression will be very important. These are the settings that we are going to talk about. Now let's go to the demo and try out some of these combinations. Here we are in SQL Server Management Studio. Let's take a backup. This is a T-SQL statement that we've seen a couple of times already in various forms. It is a copy-only backup of the Chicago parking tickets database, and we are going to save it to my L drive. My L drive is a slightly older NVMe drive, but it should still be pretty fast for this operation. Now, I will warn you, I'm not going to care particularly about finding the fastest database backup time for Chicago parking tickets. It's a small database that completes in seconds, and there is going to be some amount of noise in the results, simply due to whatever else is happening on the system at the time. If your largest databases finish full backups within a minute or two, it's unlikely you're going to gain much from tweaking their settings. This is more for people whose full backups can take dozens of minutes or even hours. Before I take a backup, let's turn on a few trace settings. These come from a Bob Dorr blog post from 2008, but they still work today. These trace flags will enable us to see a lot more information in the SQL Server log regarding our backup operations. Now that I've enabled these trace flags, let's take that backup. It is going to take a few seconds to complete. In the meantime, I can drill into the management folder in SSMS, navigate to SQL Server logs, and open up the current log. Inside of there, let me scroll down to when the backup started. Now, reading from bottom to top, we can see a lot of information on the backup operation. I'll point you to the buffer count line, which tells us that the default buffer count is 7. In more recent versions of SQL Server, there is a somewhat dynamic calculation for buffer count, where the size of the database can come into play as well. Our max transfer size is 1 megabyte, which is the default when you're backing up to a database that does not have transparent data encryption enabled, and you are backing up to disk. If you do have TDE enabled, or if you are backing up to a tape or virtual device, the default for max transfer size will be 64K. This also gives us the total buffer space, 7 megabytes. That is the number that matters a lot more than the specific buffer counts or max transfer size. Now let's try another setting. I am going to enable backup compression on this. That's easy to do. We'll add the compression attribute, and we can run this again. In the case of Chicago parking tickets, this will shrink the database backup file from approximately 16 gigabytes in size to just over 8 gigabytes. But we can also see that it is taking longer to complete this backup due to the compression. In this case, with my direct attached NVMe and writing one file, we might think, oh, compression may not be the best answer. Now, I'm going to remove compression for now, but I will come back to it later. Spoilers. Let's try out max transfer size and buffer count. I am okay with a 1 megabyte max transfer size, and we'll set the buffer count to 128. Then I can run this command and it will override the defaults, using 128 megabytes of memory to take my backup. We can see that it's taking just about the same amount of time as my default backup. But let's get a little cheeky and turn back on compression. If I run this command, it should take somewhere around half of the time that an uncompressed database backup took. This is an interesting finding, and it tells us we didn't throw enough RAM at the backup the first time around, and this was the likely culprit for why compression took longer with the default settings. The other setting we care about is number of files on disk. So far, I'm only writing one file, but let's see what happens if we write multiple files. Now, I'm going to kick off this script that writes 6 separate files for the full backup, all of them to the same NVMe storage. I will admit that performance hasn't changed much here, and it's within the margin of error versus a single backup file. But again, as databases get larger and I have more to back up, we could see some improvement here, as there is a throughput limit in how fast SQL Server can push bits over one file stream, and your hardware may be able to support more than that limit. So opening up additional file connections could make use of resources that were otherwise sitting idle. And we could also write more files to other drives as well, distributing that load. I won't run through any scenarios like that simply because I expect we've hit the floor of what we can achieve. And we can actually see what that floor is by writing to the null device. With these particular settings, I can read and process all of the database pages in just about 4 seconds. This takes the writing portion completely out of the picture, so we see a marginal increase of approximately 1 second in writing the file to disk. If I had zero cost writes to a single disk or striped across multiple disks, I could shave off up to 1 second. Basically, given these max transfer size, buffer count, and compression settings, adding more files won't be able to help me very much. Now, this leads to a tricky question. How do we know what settings we should choose? Well, I'll talk about that a little bit in the outro. For the time being, I'll simply say that the answer is a process rather than an exact set of values. Before we wrap up this video, let's see how we can configure backup settings in DBA Tools. First, let's import the DBA Tools module. Then, we're going to back up the Chicago parking tickets database. Let's take a peek at each of these settings. We will back up to the L drive, just like in T-SQL. This will be a full copy-only backup that we will compress. We have set the number of buffers to 128 and the max transfer size to 1 megabyte. Note that in PowerShell, we do not need to use the exact number, the integer value. We can instead use terms and units like megabyte. Finally, we specify 6 files. What's nice about DBA Tools is that I don't need to specify all 6 file names. It'll auto-create the file names for me and ensure that they are unique. Running this, it'll take just a few seconds to complete. And I think that's going to do it for this demo. Let's go back to the classroom so that I can wrap up this video. Welcome back to the classroom. At this point, I want to answer one more question that I brought up in the demo. How do we know the right settings to choose for buffer count, max transfer size, and file count? This is where I have some bad news. I can't give you exact answers. The answer will depend on your hardware and situations. I chose 128 buffers and a max transfer size of 1 megabyte, but in this case, I didn't do any kind of conclusive analysis to determine this. However, let me steal a page or two from my Optimizing Backups Using Data Science Techniques talk, as well as some additional insight since I've delivered that talk that may help you. On the big board, I have the 5 settings we might care about: block size, max transfer size, buffer count, number of files, compression. Suppose I wanted to attempt an exhaustive review of all 8 valid block sizes, 7 valid max transfer sizes, a sampling of 8 buffer counts, up to 12 files, and compression on or off. Multiply that together, that's 10,752 separate backup options. If it takes me 10 minutes to back up the database, which is on the low end of what I'd actually spend effort trying to tune, this is over 100,000 minutes, or just under 75 days straight of backups to figure out the best combination. I don't know about you, but I don't want an answer 75 days from now. I want an answer today. But there is some good news. First, as I mentioned in the intro, we don't actually have to care about block size, so throw that out altogether. Second, I recommend setting compression on. That cuts down our count to half again. A third, don't worry so much about max transfer size. Instead, just think of this as total buffer size. Fourth, pick a range of buffer count from 32 up to maybe 256. I don't think you would benefit much going above 256 megabytes of total buffer space. Next, choose even numbers for files, under the principle that you're probably not going to find a radical difference between 6 and 7 files. So let's rewrite this board just a little bit. Now we have 5 buffers and 7 files for a total of 35 backups. Instead of 75 days, we could finish this up in 6 hours, assuming that, again, each backup averages 10 minutes in length. This is a problem that sounds a lot more tractable. And that was our discussion of backup tuning settings. This is a part of the backup process that I think a lot of DBAs don't know much about, so hopefully this illuminated the options for you and gave you some idea of how you might try it out in your own systems to figure out what the optimal numbers are for you. In the next video, we will back up to the cloud, both AWS and Azure. We'll have links and show notes in the description below, and until we see each other in the next video, take care.